Hi 111. So this is going to be our second video for section 1.2. We're going to be talking about a few of those important graphs that we're going to be working with for the rest of the term now that we start building our library of functions. So just to recap a little bit, you should have a few graphs already in mind for a few specific kinds of equations already, and I just want to make sure we're all clear on those before I start adding to that list. So here's a few graphs that you should already be familiar with. So let's see, for example, what if I ask for the graph of an equation that looks something of like the form like this. So maybe for our first one here, number one, we'll do anything of the form where it's like y equals a number, right? Okay, so that's a specific equation for, and I wrote it kind of, this is not sophisticated math notation, but for example, something like, if we write example here, maybe something like y equals 3, or maybe y equals -2, where something it's like y equals a real number, something like that, right? The graphs of these are always the same, and remember, these will be graphs which are going to be, again, there's still going to be a collection of points, right? It's going to be the collection of all the points that satisfy this equation. Now, if we think carefully about it for just a second, what are the kinds of points that would satisfy this equation, right? If I was going to think of a point, a point x, y, right? And of course these need to be numbers, right? If I was going to think about a point here that was going to satisfy this equation, well, the only thing this equation actually cares about is the fact that the value of y is 3. Does this equation actually even care about the fact that x is a number? Is there even anywhere to put an x if you were going to try to say an unordered pair satisfied that equation? There's not even anywhere to put an x, right? This equation doesn't care what the value of x is. It only cares that the value of y is 3. So for example, if I wanted to say, use the point, how about the point 1, 3? Would that point satisfy that equation? Yes, because the value of y is 3. Also, another one would be 0, 3, right? And another one would be 4, 3. And another one would be -5, 3, right? And if you think about what all of these points are doing, right, they're all moving left or right by a certain amount, right? Over 1, up 3, nowhere left or right, but up 3, over 4, up 3, back 5, up 3, right? All these points are sort of, if you think about the graph, they're all sort of moving somewhere left or right, but they're all going up 1, 2, 3, right? So we're going to get a bunch of dots like this, sort of moving across like this, right, in this line, right? And so anything of this form where you have an equation where it's y equals a number, that's always going to be a horizontal line, right? So these graphs are always horizontal lines. Right? And the reason for that is because that all those points right there all satisfy the fact that y is 3. And the same thing would be true if you graphed this line right here, right? This one would be a horizontal line, and it would be down 2 units below the x-axis, right? So this one here would be something like this, right? It would look like this. It would be a solid line, of course, like this. And this one, y equals 3, would be a solid horizontal line there at y equals 3. Okay, so that's one equation you're probably already familiar with. A second one would be an equation maybe of this form. Okay, this is kind of similar to the first one. This is x, instead it's x equals a number though. For example, maybe something like x equals 3, or maybe like x equals -2, right? These are two different examples again. Okay, and similarly, the same thing would hold for this one. This equation only cares about those ordered pairs for which x is 3, right? It doesn't care what y is, right? So as long as your x coordinate is 3, you can put whatever number over here you want, and that point is still going to satisfy that equation, right? 3, 1, 3, 1,000. Doesn't matter, right? 3, -52. Right? All of those points satisfy that equation because the equation only cares that the x value is 3. And if you start thinking about what these would look like when you plot them, all these points say to go over 3 units and then go up or down by various amounts. You can go up or down however much you want, right? Because the y part doesn't matter. So all of these points, I'm sorry for the crooked axes here, but all these points care about is that you're 3 units away from the y-axis, right? You move 3 units away, go up or down however much you want. So this equation is going to graph something that looks like that, right? And similarly, this one would be the same, right? It just cares about the fact that all of the, ooh, look at those. Those are super straight lines. Wow, that's amazing. Sorry. This equation only cares about the fact that the x coordinates are all -2, right? So all the ordered pairs for which x is -2, and so that's everything here. Oops, not colors, right? And so that would be this line here. So notice these, when it's x equals a number, these are all vertical lines, right? And I'm really proud of that one. That one's really good. 2 thumbs up for that one. So that's another kind of an equation that you should already sort of be comfortable with. Let's see, let's try a third one. So anything of this form, y equals mx plus b, right? This is again another form of a line, but now these are lines which are not necessarily horizontal or vertical. And these are things that you covered maybe in Math 65, right? And this is what's called a linear equation, right? Okay, a linear equation because the graph is a line, right? And so there's certain parts of this that are really important, right? We have the fact that m here again is the slope, and that's synonymous with, again, the steepness. And b is the y-intercept, and you know exactly what that means now, right? The place at which the graph intersects the y-axis. Okay. If in fact you need to review linear equations, I suggest reviewing section 1.4. And I'll be giving you some suggested problems to review in that section if you think that you do need to review that section. So we'll just say problems to be announced. And be sure to ask me for those, just in case I don't get them to you at the beginning of class or something, in case it just slips my mind because we're so excited about starting problems. But I have some review problems for you for section 1.4, which covers just linear equations, just lines, okay? So if you feel like this is something you're weak at, it would be a great idea to look over this section right here, and I'll get you some problems for that. Okay, one more that you should be comfortable with. And this one is just our straightforward parabola, y equals x squared, right? And I think you talked about this one at the very end of 65. At least in 95, you should have talked about this. So y equals x squared, this is what's called a parabola. And as it's written, this parabola, as it's written here, x squared, just looks like this. Okay, and it has some important features, and we're going to talk more about the parabola. We'll talk about it in depth, right, in this course. But for right now, it's just important that you know that this graph right here looks like this, right? It has this little sort of nice going up in each direction, and we graphed it on our calculator before. And it passes through the origin right here. Remember, it passes through 0, 0, right there. Okay, so those are the 4 that I'm hoping that you are at least familiar with at this point. Let's now add a new one. So number 5, this one's new. Okay, and this first one that we're going to add is the equation y equals x, now not squared, not to the first, nope, to the third. Ooh, higher power of x. Okay, well, let's make use of this technology we've got here to try to get a handle on what exactly this is going to look like. So let's turn our calculator on, right, and let me get my key press history up here so that you can see what keys I'm pressing. Okay, so let's turn our calculator on, and let's do y equals here, and let's do x to the third. Now remember, this caret right here is an exponent, so we can do caret to the third. There we go. So that says x to the third. Also, we can say that as x cubed. That's totally fine. Y equals x cubed. So let's go ahead and hit graph, and we'll see what we get. Oh, that's nice. Okay, so notice we get sort of a starting down low, and it's kind of skinny, right? Starts down low, comes in, and then quickly goes right to the origin, and then goes right back out, right? And if we want to zoom in a little bit, we can hit zoom and zoom in on number 2. Here we can just hit 2. And remember, when you ask to zoom, it's going to ask you where you want to zoom, right? I do want to zoom in at the origin because that's a place of interest for us, what's going on there. So let's just hit enter to tell it that that's an okay place to zoom into. Nice. And so here we see that coming into the origin and then going right back out, right? So let's see exactly, let's make a little sketch of this, right? And so we've got this action where it's coming in, and that sort of goes down, and then it goes back up, right? And if your graphs are not perfect, that's okay, because guess what? Mine aren't either. But let's just see a couple of interesting things about this. What are the x and y intercepts here? Well, notice that it passes through the origin, right? So the x-intercept is at 0, 0, right there. The y-intercept is at 0, 0, right? So the x-intercept is 0, the y-intercept is 0, right? So we can just write x-intercept is 0, 0, and so is the y-intercept. And later in another section, we'll be talking more about some interesting things that this graph has, like symmetry and other stuff. But for right now, we can just talk about basic features like intercepts. Notice that this is only in quadrants 1 and 3. Remember, we talked about that in our first video about the xy plane, right? So that's quadrant 1, 2, 3, and 4. So it's in quadrants 1 and 3. That's important. Okay, so for right now, that one's good. Let's try another one. Let's do 6. This one's also new. So this equation looks like this: x equals y squared. Well, this one you're like, well, this one looks a lot like y equals x squared, but it's a little different, right? It's the y that's actually being squared here, not the x, right? So that's different. Well, let's try to graph it. Let's see. Let's go to our calculator and we hit y equals. Okay, let's clear our key presses here. Okay, so let's see. If we were at x equals y squared here, well, how do we enter equations in our graphing calculator here? We have to have y equals, and we don't have y equals. We have x equals y squared. Oh, that's trouble. Okay. Well, maybe we should use some of our plotting techniques to try to graph this one. So maybe let's make just a quick little table just to see if we can get some points. So remember how to make a table, right? You have x's and you have y's, right? And so let's just pick some values for x or some values for y, and then let's see if we can get some ordered pairs to satisfy this equation, points that would be on the graph. So let's just start out. Let's just do, how about something like, how about we usually do like something like -2, -1, 0, 1, 2. And let's see what happens. So if x is -2, then that means we would have -2 equals y squared. Okay, so let's think for a second. Is it possible for y squared to equal a negative number? Oh, no, that's not good, right? So what that means is there isn't a y that I can put here, so when you square it, you get -2, so there's just nothing. Nope, bad. Same thing's going to happen for -1, right? If I put a -1 right there, it's still going to be bad. Okay, so that's nothing too. Trouble. What happens if we put a 0? 0 equals y squared. Well, what can you square that gives you 0? Well, 0. So that means y's got to be 0 also. We have a point. The point is 0, 0. Great. Okay, what about if I put a 1? 1 equals y squared. So if 1 equals y squared, what could y have been so that when you squared it, you get 1? Well, that means y could have been plus or minus 1, right? So it could have been plus or minus 1, right? Because if you take the square root of both sides, you would get plus or minus 1. Okay, what about 2? If 2 is y squared, well, if you square root both sides, you're again going to get a plus or minus. And if you square root both sides, you're going to get y is plus or minus the square root of 2. Okay, well, that's good. What about if x is 4? If x is 4, 4 is y squared, well, then what? Y could have been plus or minus 2, right? Because if y is 2, 2 squared is 4. If y is -2, then -2 squared is 4. So we get plus or minus 2. Okay, well, let's think about graphing that and see what it would look like. So let's make our little axes over here. Okay, nothing happens if there's any negative x's, right? So we're not graphing anything over here on the left side. We know it passes through the origin. So there we go, got a dot there. We know it passes through 1, 1. Try to keep that from popping up. And let's see, it passes through 1, 1 and 1, -1. So 1, 1 and 1, -1. There we go. And that one's kind of hard to graph, so let's hold on to that x equals 2, 1 for just a second. But when x is 4, 1, 2, 3, 4, then y is 2 or -2. So there and there. Darn colors. 1, 2. There we go. So what happens is when we connect the dots is we get something that looks like this. And it's a parabola, but it's actually turned sideways. And notice that's sort of consistent with what you noticed here in that you were like, well, it kind of looks like y equals x squared, and that's a parabola. But